Okay, so hello and very good morning, my dear students. We are meeting after a long time. So, as we have completed relations and function chapter, now we are heading to the next chapter, and that is the last chapter of section A, that is probability. All right, so let me clear you uh, the reduced topics in this particular chapter. That is, if you can see the random variable, from the random variable till just wait till binomial distribution, the topic has been exempted, so we don't need to do. Till Bayes theorem we will be doing. Let me clear you the exercise number also, that is up to 10.5 we have to do. 10.6 will be exempted. So let's start. That is probability. We'll discuss some general points of the probability. We'll not discuss whatever we have done or whatever we have seen up to 10th class, because uh, because you're in the 12th class, as you have passed from the 11th, so you know a little bit about the probability. So I want to give you an introduction that in our daily life we come across with some situations for which we do not have any definite answer, although we know what the possible results are. For example, like whenever we toss a coin, it is certain that it will come down and it may turn up a head or may not turn up a head. When a die is thrown, it may turn up a particular number. Say, for example, we say 6, 2, 3, like that. Or if I say it may rain today. So you can see that there can be possibility and there cannot be a possibility. Okay, so this aforesaid situation predicts the uncertainty. Therefore, all are referred to as a phenomena which may or may not occur. Okay, the probability estimates the degree of uncertainty regarding happening of a event or non-happening of a event. Okay, certainly we go on finding for the happening of the event. All right. Then we come to the next phenomena, that is experiment. What do we mean by experiment? An operation which gives some outcomes under some given condition, we can call it as a experiment. Say for example, like tossing a coin is an experiment having the two outcomes. If we'll toss the coin, we'll get two outcomes, that is head or tail. Throwing a die is an experiment with six outcomes: 1, 2, 3, 4, 5, 6. Let me clear you one thing, that we call die and dice. Die is a singular form and dice is a plural form. So remember this thing. Okay. Then comes the sample space. We know about sample space. Okay, set of all the possible outcomes of a random experiment is called the sample space, and it is denoted by usually by S, or sometimes in the other book it is represented as this ohm sign. Okay, this is Ohm's sign for the resistance we use in physics. No, that is okay. Then event also, we know this, we have seen in 11th class, I guess. Okay. Okay, then comes the independent and dependent event. Two events, say for example A and B, they are said to be independent if the occurrence of A does not depends on the occurrence or non-occurrence of the event B. Say for example, in a card, that is a deck of 52 cards. It is say for example, I'm taking one card from it. Okay, so that is a independent event, because if ever I take one card from that deck, okay, it is not depending on the other. All right, so this is called a independent card. Okay, independent event. And dependent event means which is dependent. All right. Then comes the equally likely events or equally likely outcomes, that the events are said to be equally likely when we have no reason to believe that one is more likely to occur than the other. Each of the possible outcome has equal chance of occurring, means that if you have seen, no, in cricket they do a coin tossing. Why they do the coin tossing? Because there are two teams, and among two they need to decide that who will bat or who will ball, so they do a coin tossing experiment, which is a equally likely outcome, because the probability of getting head is equal to the probability of getting tail. Same case is in the die also. The probability of getting 1, 2, 3, 5, or 6 is 1 upon 6. So that is why it is called equally likely outcomes. Then comes the exhaustive events. The two events are called the mutually exhaustive event if their intersection is phi. Okay, that is no, sorry, exhaustive event if you have event E and event E1, E2, and if you go on finding the union N, if ever you get the whole sample space or the full, that means whatever experiment outcomes you got, that is called the exhaustive event. And mutually exclusive event is that if you have two events E1, E2, and their intersection is phi, that is called exclusive. Okay, exclusive means a newly, or what we say, that is they both are totally different. So these two events on doing their intersection, if we get phi, then this is called mutually exclusive. And two events such that on taking their union, if we get full sample space, this is called the exhaustive. Now events are some events are like they are like both, they are mutually exclusive also and exhaustive also. Okay, let us take one example of it and we'll understand through one example. A very best example we can understand. Suppose we have a well shuffled pack of 52 cards. Okay, and I'm considering four events: E1, E2, E3, E4. E1 says drawing a spade. E2 says drawing a club. If you could remember, spade looks like this, club looks like this, hearts, it looks like this, and hearts, and one more is what, diamond. Don't call it as we'll take just a group of spade, club, hearts, diamonds. They all are what, head count of 13 cards in them, right? Now see, this E1, E2, E3, E4, if I go on finding the union of them, what does the union says? We have to sum up. So after summing up, I'm getting the 52 cards. That is what I'm getting, my full sample space, because I'm considering S as a pack of 52 cards. Are you able to understand this? So their union will give me a full pack of 52 cards, which is nothing but the S. Okay, now if I find the union, sorry, intersection, E1 intersection E2, or E2 intersection E3, or E1 intersection E3, anything. So is there any common between spade and club, club and hearts, hearts and diamond, spade and diamond, club and diamond, hearts and diamond? No. The answer would be phi. So can you understand that this is a very good example to understand the events can be mutually exclusive and mutually exclusive. And summing up the definition, it is said to be called mutually exclusive and exhaustive. All right. Now coming to the next topic, that is odd in favor and odd in against of a event. See, I'm just giving you a basics about it. Okay, so let E be an event and there may be M outcomes favorable to event E and N outcomes unfavorable to E. What I said, let us consider an E event in which we are giving M as for the favorable outcomes and N as for the unfavorable outcomes. Then odd in favor, what does the odd in favor says? Number of favorable outcomes upon number of unfavorable outcomes, means M by N. And odd in against, the number of unfavorable upon number of favorable, which is nothing but N upon M. So please remember this thing. One more thing, probability of happening plus probability of not happening is always equal to 1, which says the total probability always remains 1. This is also called the this is we have seen in the 10th class, no, one axiom that the total probability is always equal to 1. This is also called the complementary event. The complement of E is E complement and their sum is 1. Okay, now next comes the additional theorem on probability. Okay, what it is? Additional theorem of probability. Okay, so addition theorem on probability. Let E1 and E2 are two events which are associated with some random experiment. Okay, then the probability that at least one of the two event E1 or E2 will occur is given by probability of E1 union E2, which is nothing but, okay, first of all let us understand additional theorem of what I told, that if we are considering E1 and E2 be two events which is associated with some random experiment, then probability that at least one of the event E1 or E2, see, or they are saying, this is very important word, or, for or they are using union. We know that the formula of probability of E1 union E2, we know the formula of E1 union E2, that is probability of E1 plus probability of E2 minus probability of E1 intersection E2. In the 11th class, in the set chapter, we have seen the number of E1 union E2. Now in this probability chapter, you only need to add probability. So probability of E1 union E2 is this. In the 11th class, we have seen this thing. Okay, now if we want to find that even for E1 or E2, so for this or case, always remember if the events are mutually exclusive, so for the exclusive case the intersection is phi. So finally we can say probability of E1 union E2 is probability of E1 plus probability of E2. All right, this is very similar for the 3 events, 4 events. This will be plus probability of E2 plus probability of E4, whatever, or how many, whatever be the number of events you have in the situation. Okay, so this is called the addition theorem on probability. All right, so with this we are starting the chapter. As you can see, you have the laws of probability. Okay, so there are some theorem like if A and B are even associated with a random experiment having sample space S, and if A is a subset of B, then if A is a subset of B, A is a subset of B, then probability of A is less than or equal to probability of B. This is the first axiom. All right, and the second axiom says that probability of B minus A is probability of B minus probability of A. So do remember these two axioms. Then I've explained you mutually exclusive events, then addition theorem on probability, and there are some formulas, or we can say they've named as theorems. If A and B are two events associated with the random experiment, then what are the formulas there? This formulas you are well versed, as we have seen this in 11th class. The different formulas of A union B. This can be written as probability of A minus B plus probability of B minus A plus probability of A intersection B, or else we can write probability of A union B as probability of A plus probability of B minus A, or it can be written as probability of B plus probability of A minus B, and so on. So please note those points there in the copy. Okay, and for the theorem fifth, probability of A union B union C, so that can be written as probability of A plus probability of B plus P of C. Okay, I'll call P of C P of A. So please understand that is probability, because it is very tedious to say again and again the probability of A and probability of B. Okay, so P of A plus P of B plus P of C minus P of A intersection B minus P of B intersection C minus P of A union C plus P of A intersection B intersection C. Okay, Venn diagram is also drawn there at the end, so please have a look. Now let us start with some illustrative examples. So as I can see that we'll do some questions, because see, these are based on the basic formulas. Okay, so they are very easy to do. Let us do some questions of it. Okay, so let us take this question. We are given with probability of E is equal to 1 upon 4. Probability of F is given 1 upon 2. And we are given with probability of E and F is equal to 1 upon 8. Now let me clear you one very, very important thing here. See, if you are given E and F, then for the AND, we always use intersection. And for this C, E or F, we take union. Okay, so for AND we go for intersection, and for OR we go for union. Okay, please remember this thing. Now so this is fine, this is nothing but intersection, and this is nothing but union, and this is intersection. So probability of E union F is required. This is the required probability. So we know this is probability of E union F. This is P of E plus P of F minus P of E intersection F. So P of E is 1 upon 4. P of F is 1 upon 2 minus P intersection P of E intersection F is 1 upon 8. 1 by 4 plus half is 3 by 4, we know. Okay, so to make the denominator same, we can multiply this by 2. So 6 minus 1 by 8, this will give you 5 by 8. So this is the answer. Second, probability of not E. Not E, do you know? This is E complement. Intersection F complement. So E complement intersection F complement. Can this be written as probability of E union F the whole complement? Can you tell me that which uh, theorem or law I have used here? So if your answer is De Moivre's theorem or De Moivre's law, then you are correct. Because what does that say is A union B the whole complement can be written as A complement intersection B complement, and this can be easily verified by Venn diagram. Alright, so we need to find this, which can be written as this by De Moivre's theorem. Please write there. And we know by the complementary what we say convention, or like complementary events, this can be again written as 1 minus probability of E union F. Okay, as if you are dealing with this type of data and this type of question, we write this as 1 minus. No, you can understand, no, probability of E union F the whole complement is 1 minus we have the value of this, that is what, 5 by 8. 8 minus 5 by 8, 3 by 8. Answer. Alright, so try to do the question from fourth one. Okay, because those are somewhat important, you can say, or like. Okay, then let's come to the next question. Next question, a ticket which is numbered from 1 to 20. They are mixed up together, and then a ticket is drawn from at a random. What is the probability that the ticket has a number which is a multiple of 3 or 7? Okay, so there are 1 to 20 tickets. Okay, and we have to find the probability that the ticket which is drawn is a multiple of 3 or 7. This is OR case, that means probability of 3 or 7 we have to find. So let us consider the probability of A as multiple of 3 and probability of B as multiple of 7. So how many multiples are there? No, just event, you just take A be the event, and not, we are not finding the probability, sorry, that is A as multiple of 3 and multiple of. So between 1 to 20, what are the multiple? 3, 6, 9, 12, 15 and 18. For the 7, how many? 7 and 14, right? Now, what will be the probability of A? There are 6. 6 divided by number of outcomes, number of favorable outcomes upon total number of outcomes. 6 upon 20, which is how much? 3 by 10. Okay. Then, what will be the probability of B? It will be 2 by 20, 1 by 10. Okay, so we need to find probability of A or B, which is probability of A union B, right? Okay, probability of A plus probability of B minus probability of A intersection B. I will not do. Why? Because multiple of 3 are totally different and multiple of 7 are totally different. They both are prime numbers. Okay, so they don't have any intersection in for them. Okay, so let us just do. Okay, so in between 1 to 20 there are no common number, so that is why they both are independent even. So by that, the probability of A intersection B is 5, and that is we are excluding, so we need to only find their sum. So 3 by 10 plus 1 by 10, 4 by 10, which is 2 by 5. So 2 by 5 is the probability. You know what is the meaning of this 2 by 5? From every fifth, the 2 will always be the multiple of 3 or 7. Okay, in the lower classes we have seen that how do we understand 2 by 5. Say for example, 1 2 3 4, 1 2 3 4 5. So we used to fill this 2, and how do we represent 2 by 5? Like this. So you have to understand like this. Okay, the probability. Okay, so dear children, in the next lecture we'll solve some more question, 2 3 question of this exercise. Okay, and I'm waiting for your doubts. Please, just your doubt should not stop. Your doubt should occur, because as we have started the chapter. Okay, so we'll see the conditional probability in the next lecture. Okay, till that, do practice, just go through the examples. Okay, thank you so much, have a nice day, bye bye.